Hi everyone, thank you for joining our talk. My name is Zhisheng. I am from Baidu Security, and today I would like to introduce a robustness improvement method for object detectors in safety-critical scenarios. It is well known that deep neural networks can achieve excellent performance in many tasks, but their performance might drop when the inputs are subject to small adversary perturbations. For example, small but carefully crafted perturbation can make an image classifier think a J as a fountain. And many efforts have been devoted to improving the robustness of the image classifier, such as adversary training and feature squeezing. In the meantime, object detection models have also been demonstrated to be vulnerable against the adversary attacks. The bottom figures provide an example of misleading unit V3 to misclassify cars into trucks. However, very few efforts have been devoted to improving object detectors' robustness. But in fact, robustness of object detectors shall be equally important as accuracy. We observe that first, object detector has been widely applied to safety-critical scenarios such as autonomous driving. In such scenarios, either misclassification of the objects or the wrong location of the objects could lead to severe consequences. For example, a Tesla car was involved in a fatal crash in 2017 caused by the failure of its forward-looking camera to detect a white truck. And second, previous work shows it's possible to improve robustness of object detector via adversary training, but there is hardly any guidance of how to generate adversary examples and how to utilize them to perform the efficiency and effective adversary training. This observation motivates us to study how to practically improve the robustness of real-world object detectors. The main object can be formalized as the following min-max problem. We solve the inner maximization problem by generating adversary examples with multi-step PGD method. Then we solve the outer minimization problem by training the model on the generated adversary examples. The intuition behind our work is to augmenting the training set with adversary examples. But how to do this in a large-scale real-world object detectors is still challenging because generating adversary example can be very expensive. We propose a two-stage adversary training strategy. The first stage trains the whole model with less expensive adversary examples, and then the second stage fine-tunes the model with scenario-based strong adversary examples. The details will be introduced later. In this paper, we use Unit V3 on MS Coco dataset as a running example to demonstrate our adversary training. We choose Unit V3 because it's a representative model of one-stage detectors and widely used in self-driving scenarios. An adversary example are generated by n-step PGD with perturbation budget epsilon here in our paper. We focus on generating adversary examples that can lead to misclassification of the main objects. To measure the severity of the adversary example generated by us, we introduce success rate. The success rate is a ratio of successful adversary examples to the total number of attacker trials, which can quantify how easily an attacker can fool an object detector. The left figure presents the success rate of the adversary example generated with different budgets, while the step is fixed to be 20, and the right figure presents the success rate of the adversary example generated with different steps, while the budget is fixed to be 10. We can see from the left-hand side, as budget increases, the generated adversary example induces severe damage to the unit V3. And this indicates that the attacker has the incentive to choose larger epsilon in order to fool the object detector. But however, when epsilon is too large, the generated adversary examples are perceptually distinguishable from the original image. And the right-hand side figure indicates that the attacker also has incentive to choose the large n in order to fool the object detector. However, a large iteration number requires a huge time to consumption. The table shows that the time used to generate 5,000 adversary examples with different iterations. We observe that the time consumption increases almost linearly with the steps, while budgets barely affect the time consumption. So choosing larger epsilon might bring more benefits, and choosing as large n as possible is not always a good strategy to generate severe adversary examples. We generated two sets of adversary examples, weak ones and strong ones. The strong ones will have larger n and epsilon. Then we test the simple adversary chaining strategy, which retrains the model with weak or strong adversary example alone. The results of retrained models are shown as follows. We can see that simple adversary chaining can improve the performance under strong adversary attacks. But the robustness improvement of the model trained with a weak example is much smaller, and similar results can be found when testing the model with weak examples. Moreover, adversary training with strong examples will suffer a significant performance drop when testing with clean examples. So we propose the following two-stage adversary training strategy. In the first stage, we train the whole model with weak adversary examples. This is because object detector give prediction based on extracted features, and wrong predictions might be made based on the features before the upper layers. The stage 1 only trains on weak adversary example because generating a large set of weak adversary example can still be efficient. And to avoid overfitting, we freeze the convolution layer and train upper layer in stage 2. We only train a small portion of adversary example with large n epsilon. Such two-stage training can reduce the training time significantly, and therefore we can successfully deploy our method on UNO-V3. Here, stage 2 acts as a regularizer which punishes the model from being sensitive to the changes from weak example to strong example. So this will improve the general robustness of the model. We now show some evaluation result of our two-stage adversary training. In our evaluation settings, the population of the strong adversary example is only half of the weak examples. And after fine-tuning by the stage 2, the model performance under strong example is even better than that of the model shown in train on the strong examples. And moreover, as indicated in the right-hand side figure, there is no performance drop on clean examples. Our adversary training can mitigate overfitting and improve the overall performance. One possible reason is that stage 1 training can learn the features of the clean models, while the stage 2 training makes the model less sensitive to the adversary example with large perturbations. As introduced before, success rate can evaluate the severity of adversary examples. In the meanwhile, we can use the success rates of different adversary examples to measure the model robustness under different attacks. The results shows the success rate of different models when testing with different adversary examples. Compared with the pre-trained UNO-V3, all of the adversely trained model can lower the success rate. Moreover, the model trained by our two-stage method is the most robust model against almost all different adversary examples. These results are consistent with the MAP results shown in the previous slides. The overall robustness improvement leads us to a question: can we make the adversary training even more efficient when we focus on a specific safety critical scenario? To explore the answer, we further customize our strategy on autonomous driving scenario. We generated a set of strong adversary examples based on 5,000 images selected from the supercategory vehicle and outdoor. Compared to the previous experiment, which has about 9,000 strong examples, we save about 49% on the adversary training time. We also observe some significant improvement in detecting vehicle and traffic lights objects. Some visualization examples are also provided as follows. We can see compared to the pre-trained UNO-V3 model, our model can correctly detect some objects which is missing by the UNO-V3. I would like to talk more, but it is simply impossible to cover everything in 10 minutes. To sum up, our work serves as a stepping stone towards efficient and effective robustness improvement for large-scale object detectors. But there are still many works to be done in the future. For example, the extension of our algorithm on other network architectures such as SSD and RCN. And a common problem with the adversary training is that it only works on the attacks that it is trained on. Our two-stage adversary training partially serves as a regularizer which punishes the model from being overfitting. But how to fully adapt our adversary training on other attacks, such as faster gradient size, is still a challenge of future work. And thank you very much for your listening. And I also invite you to the Q&A session if you have any questions or even you have any comments so we can bounce ideas. Thank you.